Now, the very first approach is just the vanilla PGM, or just you do basic stochastic gradient descent using the gradient estimator that we have found, right? So what we have this term. So this expectation, the expectation of this Q times the gradient of the policy network is log likelihood, actually. That term is the estimator of our gradient. We can just sample from this, right? I can start from one initial state, and then I keep on playing with my policy network. Each time it's going to take me to a new state by doing some actions. So I have the trajectory of the states and actions, and also sample returns, values, sample rewards. So I can estimate this guy. I can find one estimator of this guy. I can compute one estimator of this guy, one sample of this guy, and then I can simply use that inside my training loop. So what does it mean? It means that I want to update my policy network. So each time I need to update it by some gradient, right? And that gradient, I do know how does it look like. This is the way that my gradient looks like. And since I do not have exactly access to those distributions and I cannot compute that expectation, I am going to just simply estimate it, right? So I would say if I am having this trajectory, I'm going over time in this trajectory, then when I am in one particular time, right, at that particular time, the estimator of my gradient is simply the estimator of my Q function. How can I estimate my Q function at one single point? Say I am at time 1, S1A1. How can I estimate my Q function at this point, S1A1? You just sum up whatever you get after that, right? So I am in state 1. I do action 1, right? Say my state 1 is this location, right? And my action is to just go right, right? And then I keep on playing towards the end. The game is over. Now I just collect whatever I just add up whatever I collected as reward from this point on, right? That is one sample return, right? And that sample return is given this fact that I was at this point and I did action right, correct? So that one is one sample of this Q function, right? At the point S being exactly my location, A being the action right, right? And you can keep on doing it again and again, right? You again come here, you just do action right, and then you keep playing, you collect whatever you got. That is another sample, right? Now, we are going to get one single sample, so the best thing I could do was that I do multiple samples, right? And I average them, so that is going to be a better estimator of that guy. But the problem is that, well, we don't have access to so much of samples, right, in practice. So I can just simply use one sample, right, like a stochastic gradient descent with batch size 1. And you do know that that one is also going to eventually work, right? So I'm going to do the same thing. So I'm going to get my single sample here. Then what is my, how can I compute this logarithm then? This gradient then? I have my policy network, right, pi. And that policy network is going to get the representation of the state that I am in, right? It's going to give me one distribution over A, right? Correct? Now, what I do, I just add one logarithm at the output of that policy network, right? And now I give this state. This is going to compute one policy, right? I also, give this state and action together, right? And it's going to give me what is the density at the particular action when I am in the state S, right? Just remember, for example, the Gaussian distribution we talked about, right? So you remember the Gaussian distribution? Maybe that one could help. Yes. Okay. So you remember the Gaussian example, right? We said that pi theta of one particular action A given a state S. This is a Gaussian distribution with a mean. So this guy was a Gaussian distribution with some mean which was computed from the representation of S by parameter theta, right? Some say theta times xs, right? And some variance sigma squared, right? For the moment, say the variance is even 1. Okay? This is a Gaussian distribution, correct? And then the mean value of that Gaussian distribution is computed from your state, from its feature representation. For example, my state is this point, and its feature representation is the coordinate, right? The coordinate of this point, times theta are the parameters, right? Everybody's cool? Okay. Now, if this Gaussian distribution is my policy, then I can write down this policy, right? This is going to be 1 over square root of 2 pi times e to power minus a, the action that I have, minus the mean value, which is this guy, theta xs, right, squared divided by 2, right? That is my policy network. Correct? Everybody's cool? Questions?
Sorry, what's the mean?
What is the mean?
Yeah.
This is mean value of the, yeah? What do you mean? Sorry, I didn't get your question. I just, it was our example. I mean, if it is easier for you, say I have one neural network. This is a neural network, okay? And this neural network has parameter theta. I give a state S to it. It's going to give me some f theta of a state S. Okay? And I put the mean value here to be f theta of S. Okay? Now, this is going to be simply f theta of S, right? Everybody's cool? Now, if I want to compute logarithm of this guy, log of this guy, okay? This is going to be a log of this term, right? Log of this term, which is log of this plus log of this, right? Correct? What is log of this guy? Exponent, right? So it's going to be a log of this term minus that, right? Correct? Everybody's cool? So log of pi theta is going to be a log of this term minus that exponent, right? Now, I want to compute the gradient of this guy with respect to theta, right? Gradient of this guy with respect to theta, what is it? 0, right? So I need to compute the gradient of this guy. So minus comes here. Gradient of this guy with respect to theta, right? How can I compute the gradient of this guy with respect to theta? I use chain rule, right? So I'm going to write it down. So let's think about computing this one. This is going to be minus 1/2. First, I'm going to compute the derivative with respect to f, right? Correct? So that is going, I mean, the minus is going to disappear. It's going to be a minus f theta s, right? Times gradient of f theta s, right? Everybody sees what I'm doing?
1 over 2 also.
Sorry?
The 1 over 2 should also.
1 over 2 is here.
Yeah, shouldn't it always also be?
Oh, it disappeared. Sorry, 2 times that. Right, sorry. Okay? Everybody's clear? So gradient of this guy, gradient of this one, which is 2 times this term times minus 1. So it's going to be a times that one without minus. This is the term. And this is the other term, right? The gradient of the inner term, right? How can I compute this guy? Say the magic word. Backpropagation. Great. So you're going to do backpropagation on this guy, right? So you put your state here, right? Your state goes through the neural network. It's going to give you some f, right? Then you're going to backpropagate over this guy. Gradient of f theta s, right? This term is given, right? Also, you do know what is your action, right? Because you acted, right? So you have a. You have also f theta s, right? So you computed that term. Everybody's cool? You see what we are doing? This is possible, right? It's not just science fiction. It's really happening, right? So when we sample one trajectory, for every single point, we can do that, right? So the state that we are in, you just give this state to our neural network, it's going to go to the output, then we do back propagation, then we are able to compute this gradient, right? There is no problem, right? What about Q? Again, for the Q, we can simply, as I told you, take the sample output to be sum of rewards to be my estimator of the Q value, right? And then I have this guy. This is one sample estimator of the term inside the expectation. I simply update with that sample, right? And then I go for the next time, right? I go for the next time. Again, I'm going to say, OK, let's see what I have collected in the future. Then I take them, add them up. This is a sample Q. What is the gradient? Forward, backward. This is the gradient. I put it there. I update, right? And every time I go in my trajectory, I can do one update, right? That was cool? So this is going to be the vanilla version of the policy gradient method. So you basically start with one trajectory. This is your trajectory. And when you go inside the trajectory, every time you get one Q estimator, right? Now I'm writing here Q estimator because I don't want to specify the way that you are estimating it, right? Maybe you come up with your own idea. The most simple one is to just do Monte Carlo, right? But maybe you come up with some weird idea. Not that I believe that you should come up with some weird idea. No, because we are going to replace it later on with the value network. So we're going to have one network which is going to do this job for us. OK? Later on when we do actor critic. But right now, I don't want to talk about that, right? So I'm going to say that let's assume we can do some estimation, right? And if I get this estimator, then I'm going to update using that estimator in this form. This gradient, this term, is something that I can simply compute by back propagation on my policy network. I do not have to do any trick, right? And this is the most important thing. I have some way to compute a gradient. Questions? OK, so if you think of this one, this is basically what we had in the reinforced, right? The reinforced algorithm that I showed you, we initially started with the trajectories. We ended up with one expression for update. Then I told you randomly that, OK, instead of that term summation of g of the trajectory, just replace gt, the sample return. And then it's still going to work, but the reason is simply policy gradient theory, because that gt is also an estimator of qt, right? gt is sample return. It tells you at time t, whatever you get after that, right? That is one estimator for your Q value at that state in action, right? And you simply use that GT inside your algorithm, right? So GT is not the best estimator necessarily, that's correct, but it's better than the estimator we had initially, to be honest. And because of that, it's going to work slightly better if you replace or PG version 1 with reinforced. Okay? So this guy is the most basic version of the policy gradient method. So reinforced was the first policy gradient method. PGM was born after the introduction of the reinforced algorithm by Williams. And now people started to say that, well, it's a very cool idea because you don't really need a value network or value model anymore. You are actually not working with the value directly. You simply have one model for your policy, and that model is just getting updated from samples. That's cool, right? This is what we think when we think about reinforcement learning, right? I have one agent which is having one policy, one strategy to play. And each time we sample, we tell it just change your strategy to that, right? And it's going to update its strategy, right? We keep on updating till it's playing with the optimal strategy. This sounds more like intuitive reinforcement learning as compared to the Q learning and other things where we work with the value network, right, or with the value model. We try to estimate the value, and then out of the estimated value, we say, OK, we play, for example, epsilon greedy or greedy, right? This is more intuitive. But the issue with this one is that when people started to work with this one, there was a bit of challenge here. So there was a bit of instability, and this was the reason that PGM was quiet, not very trend or state of the art for some long time. Like for some long time, especially when it was simply about linear models and tabular reinforcement learning, people were only working with the values because that was stable. PGM was not necessarily stable. Okay. One thing else that you might ask me is that I just showed you the Monte Carlo estimation, right? And you expected me that the next slide would be TD, right? But I'm not doing TD because I'm a very kind person. I don't want to take more of your time. No, this is not the reason. We have a bit of problem with TD here, okay? And I'm going to explain it a bit in a bit, okay? But TD is not very straightforward when you are working with a policy. Okay, let's go ahead and see what is the trouble that you might get when you do reinforce, right? Say that you take your time, you're a very patient person, so you listen to me for a long time, and you believe me, you try to implement reinforce. Then you want to try it on this algorithm, okay? On this environment. What is the story here? You have this particle, okay? And this particle is able to move in any of these three directions, okay? Now, what it wants to get to the top of the bottle or whatever that is, right? So this particle wants to go up, okay? And then at every single location that this particle is, it has one of the three choices. Either goes straight up, or right, or left, right? Slightly right, or slightly left, right? Now, I want this guy to get, this particle to get to the top in the fastest way as possible, right? This means that I want to make it understand that it should just move up, 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 up all the time, right? But I want to do it by reinforcement learning because I'm sick. I don't know. No, because I want to see whether my algorithm is working or not, right? So now, what's going to happen if I start with some random policy? So I start with this policy that is just moving in any direction with the same probability. The length of those arrows is showing the probability that your policy is giving you. So now the policy tells you just go any direction with the same chance. Now, if you do that, you might just move like this. This is one trajectory that you would get. You might do like this. This is another trajectory that you could get. And if you keep on playing, you get lots of other trajectories, right? So always you're going to go some way up, but it's not the straight going up, right? Now, the thing that you can do is that you're going to define a reward function, right? And that reward function at every single state is going to tell your particle how much reward you got so that your particle is somehow inclined to just move directly up, right? So this is one valid choice of the rewarding system. So what is that? That x is exactly the x-axis, right? So you start from here, like that direction, and you go in that direction, right? Now this is x. I don't do anything with y-axis. Now this is x-axis, and my reward is simply this one, right? Every point that I am, I look at the x value of that point, right? And then I'm going to give the corresponding reward. That reward makes sense, right? If I am on the edges, I'm going to get reward -1, right? If I am exactly at the center, I'm going to get reward +1, right? And anywhere in between, I'm going to get something in between, right? So it's going to make my particle to stay in the middle, right? Since it starts at the middle, it means they always try to stay in the middle. The only action that is sensible in this case to just directly go up, right? You don't move right or left, right? Everybody's clear? So that makes sense. If this guy is really trying to just maximize his return with respect to this rewarding system, it's going to learn that you should just go up, right? Now, one thing that you should pay attention here, what is the value when I am in the corner? -1, right? What is the value when I am at the center? It's 1, right? So it's a symmetric value between -1 and 1, right? Everybody's cool, right? Everybody sees that. Cool. Now, if you try that, you start with reinforced. This is your iteration 0, so your policy network is giving you uniform distribution in every direction. But you keep on sampling, and in every single sampling, you use that sample to update your policy, right? And once you keep doing that, then after a bunch of iterations, say, for example, 900 iterations, you see that the probability of going in any direction is roughly 0, and you are just going with probability 1 right up, right? This is what you wanted. Reinforce is working, right? Cool, perfect. That's nice, but now the next thing that you do, you would say, okay, let me just change the scale or the bias, the start point of my rewarding system, right? Instead of giving -1 when I am on the edges, I'm going to give 10. And then when I'm in the center, I'm going to give 12, right? Still, in the center, I'm getting more reward. So one intelligent particle is going to concentrate in the center, right? Everybody's clear, right? It's the same thing. Even this scaling is the same. I mean, -1 to 1 is same as 10 to 12, right? Doesn't matter. I only shifted everything, right? Now, if I do that and I start doing iterations, then you see that your algorithm or your distribution is not really symmetrically going down towards the distribution that you want. And it starts to just behave, just jump between, right? So as it starts to give more weight to the left, then it just changes its sign to give more weight to the right. It does not mean that the the main action is not getting higher chances. It's increasing in the probability. But it's increasing in the probability much, much, much slower as compared to the case where you have between -1 and 1. Everybody's clear? Questions? Yes?
Will this also not break if our particle was like over left to the right or something?
Sorry, I didn't hear you.
No, it was, I realized I was wondering if it would break if our particle started somewhere else.
Oh, no, 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 no.
It will still, like, the reward will make it go to the right, or make it go to the center, sorry.
Yes, 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 because it wants to just be in the center, right? So it's going to take it in the center and then it goes up, right? Yeah, but I mean, in this example, I assume that we start exactly center down always, right?
Yeah, that makes sense.
So, questions? So you see the problem here, right? So if I change my rewarding system simply by shifting it, then the reinforced algorithm is to start to just struggle finding out the right policy. Now, the question here is that what is happening here? So what we see obviously is that the vanilla policy gradient method is getting impacted significantly in terms of convergence when we shift our rewarding system, right? And where is the problem? If you think about the reinforced algorithm, or if you think about the general vanilla policy gradient method, where should be the problem? Which guy is making the trouble for us? How many terms we have when we are updating? 2 terms, right? One of them is the estimator of Q. One of them is the estimator, the gradient of the log likelihood, right? Which term is the guy who is impacting now? Q, right? Because the policy network is not changing in that sense, right? When we change the rewarding system, it's only Q which is getting impacted, right? So obviously the problem is this guy, right? This Q. Yes?
So you said the whole motivation of policy gradient is that we don't want to work with value, but Q is the value.
Yes. We cannot get rid of that. The key point is that we can work with these estimators, right?
But then what is the difference between that and
Oh, yeah, but by this one, I can work with the continuous actions, right?
that?
Well, by simple Q learning, I cannot do that, right?
Continuous actions.
Yes,
big
right.
motivation.
It's a big motivation, right? Exactly. So you see the trouble? So the key trouble is the Q term, right? So now, let me now just take a look at this term, right? And see what is happening here. So you see this Q term, right? And then when you have this Q term, you are just sampling from it, right? This means that every time that you sample, you get a sum of bunch of rewards, right? in this example that I have, when I have this system minus 1 and 1, right, in this case, when I start with the uniform distribution, now probably my particle once goes like, it goes to the left and then goes up, right, the first trajectory. Now here it's going to get some minus and then gets to 1, right? If I add them up all together, it's roughly around 0, right? Again, if it goes right and then goes up, same thing is going to happen, right? So this means that those samples that I'm collecting are going to be concentrated around 0, right? Correct? So they're concentrated around 0. The value that I'm collecting as a sample is concentrated around 0, randomly sampled around 0. And because of that, this Q value that I have is small, right? Is around 0. But when I change my system to this guy, what's going to happen? If it goes any direction, for example, in one of them it gets 100, in the other one it gets 150, right? So it means that the samples that I'm taking are still changing in value, but they are concentrated as around a higher value, right? A higher average, correct? So this is how it's going to show up here, because this Q that you get, when it's concentrated around a larger value, every time that you sample, you're going to get a larger sample, right? When you have a larger sample, then you're going to get more sensitive, right? It means that your gradient of the policy tells you, oh, maybe you just move a bit here, but then the Q gonna, smash it. Just take the gradient, make it like huge, right? Again, your gradient of the log likelihood tells you just go a bit that direction, then Q gets multiplied and just hugely change it, right? So if Q, for example, if Q is significantly large and it's not concentrated around 0, the thing that happens if this gradient is, for example, negative, right, then any entry which is negative is getting multiplied with a huge number, right, a large number. And this means that the value of theta is getting significantly changed, right? And if that is the case, that this guy is slightly positive, then that Q is going to get multiplied and a huge change again in the value. So the value increases a lot. The parameter increases a lot, right? Now, this is one of the very first things that you can observe, and it's going to help you understand later on the trust region story. Because the thing that is going to happen here is that when Q is very large, then the gradient itself, that gradient of the log likelihood, that term, it might be small, but the Q gets multiplied to it, and then it's going to change significantly the value of theta, right? And then the problem that is making is that theta is not directly connected to your value, right? Theta is specifying your policy. Policy is specifying your value, right? It's true that you like to have an intelligent policy, right? But at the end of the day, the way that you evaluate your policy is by using value, right? And you don't really know exactly how change of theta is going to impact your value at the end of the day, right? It's just impacting policy. We're going to talk about it more when we get into trust region. But this is somehow telling you that your policy network is more sensitive to the change of parameters as compared to a value network, right? And this is a very general behavior you always see with policy networks. Okay, so if we keep Q concentrated around 0, then probably we're going to have a better behavior in your vanilla policy gradient method, right? So this means that if I had that rewarding system 10 to 12, I already just subtract everything from 11 first, right? So I concentrated around 0, then I work with that system, right? And this is eventually going to work better as compared to the system 10 to 12, right? Everybody agrees? Everybody sees what I'm saying? Right? So the key point here is that we need to just keep this Q, this estimator, to be concentrated around 0. But if I want to keep it concentrated around 0, maybe the rewarding system of my environment, I mean, it's not in my hand that I always design it, right? I mean, the dummy example we had, I could do it, but maybe this is coming from a natural environment, right? And then in the policy gradient result that we had, the policy gradient theory, we really needed to have this estimator of Q, right? You really need Q term, right? Because it's Q who is showing up behind the gradient of the log likelihood, right? You might tell me, okay, if I want to just concentrate Q around 0, this means that I should get my Q and subtract it from something else, right? So I am just shifting it. I am adding a bias to it, right? And I'm not working anymore with Q itself. I'm working with a bias of it, right? A bias version of it. And how you can guarantee that the policy gradient method is again working if I replace Q with a shifted version of it? The key point is that you can actually show it. Actually, you can show that whatever you do as a shift, it's not going to impact your gradient. So, now, let me just try to make it clear for you why you can shift your rewarding system as you wish when you're working with a policy network. So, let's say that we have this gradient term, which is coming out. So I have this policy pi theta, and I am playing with this in my environment. Okay? For now, say that I have a genie. This genie just looks at my state, my action. It's going to give me the Q value. Okay? You don't really need to estimate anything. Okay? Everybody's cool? Now, the thing that I'm going to do now is that I'm going to get this Q, so whatever my state is, whatever my action is, okay? I'm going to give that one, I'm going to get from the genie Q value, right? This is the term here. And now I do one thing else. I do not look at the action that I have done with my policy. So the policy is aside. The only thing that I do, I look where I am. What is my state, right? And I have one function, one arbitrary function, U. I just give the state to that function. It's going to give me one value, right? So that value, that term U, that bias term, say, is depending on my state, but it does not depend on my action, right? So it means that if I am here, right, it doesn't matter which direction I go, always I'm going to get the same value for U. But the value for Q is going to change if I change my action, right? Again, I come here, the value of U is changing as compared to the previous one, but it does not, again, depend on the action that I do, right? Everybody's cool, right? So U depends on this stage. Q depends on both state and action. And I built this Q prime, which is not Q itself, right? It's a biased version of Q, right? I'm going to use this one. Now, instead of using Q inside my policy gradient theorem, I'm going to use Q prime inside that. I want to see how my gradient of the objective, the gradient of the J that we initially calculated, how does it change? Okay? Everybody's clear? Good. So I had this expectation, right? The expectation, I guess I'm not getting rid of, no. Okay. The expectation, just ignore whatever you have as subscript right now. Now, instead of Q, I am replacing Q prime. And then I have gradient of my log likelihood. Everybody's cool? Now, let me just open it up. So Q prime is Q minus U, right? Q depends on the state and action. U only depends on the state, right? Everybody's clear? Okay. Now, next step. Well, I am going to open up this expectation. The expectation, look at the second line. The expectation is first taken with respect to A, given the state that I am in, right? Using my policy. And then is the expectation with respect to a state itself, using my weird distribution D, right? Correct? So I can do this expectation step by step. So I can say, whatever term I have inside, I first take the expectation with respect to A. This is what is inside. And then whatever I get, that is only depending on my state. I then take the expectation with respect to state. Everybody's cool? Questions? I mean, trust me, it's going to be very simple now. It's going to get, like, just magically everything going to disappear. Okay? Now, next thing. This term that you see inside the brackets. So I have brackets Q minus U, right? Correct? So Q times the gradient, I have it, right? U times gradient is the next term, right? Everybody's clear? Questions? Okay, now, the first term is Q times gradient of log, expectation with respect to policy, expectation with respect to state. That term is simply the term you had in your policy gradient theorem, right? That is the right gradient that you need. The blue term that you see is the gradient that policy gradient theorem tells you is the right gradient to use if you want to update your policy network, right? But what you have is that blue gradient minus the second term. Everybody's clear? So what is the second term? The second term is U times gradient of your log likelihood, right? The expectation is taken first with respect to the action, then with respect to state. When I take the expectation with respect to action, does U get impacted? What is the expectation of US with respect to A? It's US itself. What is the expectation of 1 with respect to a Gaussian distribution? Is 1, right? A constant number is coming out of the expectation, right? So this is why I put U outside the expectation with respect to pi, right? You see it here? So U does not depend on A. This pi is only distribution of my action, right? So it's going to come out, right? Everybody's cool? Now, what I am computing here is the expectation with respect to state U, that bias term, this other expectation with respect to policy. Let's go ahead and see what is this term, okay? So this is what I wanted as the gradient. This is what I'm computing if I replace my Q with Q prime, if I shift it to just make the rewarding system concentrated around 0. And in this case, I am going to have this extra term, okay? Cool. Now, let me do that. So let me just clean up everything for you right now, and let's just work with random variables, basic random variables, okay? I have this x, which is distributed with some distribution p theta, okay? What is this p theta is actually my pi theta, right? But I want to just make the notation easier right now. And now what I want to compute the expectation with respect to pi theta, this gradient of the log, right? So if I want to interpret it into a simple problem, I can write it down in this form. I can say I have x, its distribution is p theta, and now I want to know what is the expectation with respect to p theta of the gradient of this log probability, right? It's the same thing if I replace p theta with pi theta given s, right? I didn't want to have that given s. Maybe that makes a little bit of help in terms of notation. Right? Okay? So look at this problem. I want to solve this problem. Okay? Everybody's cool with this problem? The thing that I want to do? How can I compute this expectation? What should I do? I get the term inside the expectation. I multiply it with p theta, and then I marginalize over what? X. Great. Everybody sees that? So this expectation is simply this guy multiplied by p theta average over x, right? Now, let me first write down this gradient. I am actually getting back to what I did in log trig. So gradient of log p theta is gradient of p theta divided by p theta, right? Now the next thing that I do, I multiply this guy by p theta. P theta going to cancel out. This is going to be the gradient of p theta, right? Averaged over x, right? Now, what is the gradient term? The gradient term is taken with respect to theta. Everybody sees that, right? You can ask questions, you know. Everybody sees what I'm doing, right? The gradient is with respect to theta, right? What is the integral with respect to? What is it? Everybody? X, right? Now, can I change these two guys? Can I do it? Yes or no?
Can you have, like with respect to
First, do the integral over x, then take the gradient over theta. Can I do that?
yes, I guess I'm wondering why we wouldn't be able to.
Yes. Okay, perfect. Okay, so we're on the same page. So I can simply change them, right? Correct? So I can simply change. I first take the integral with respect to x, then I take the gradient, right? What is the integral of a distribution over its argument? 1, right? Doesn't matter what is theta? No. Then what is the gradient of that guy? 0. I told you I know magics. So this is 0, right? This means that the second term you had is 0, right? So this expectation is simply 0. This means that that second term that we have, expectation with respect to pi theta of that gradient of log likelihood is simply 0, right? Everybody's cool? So what does it mean? It means that if you replace your rewarding system with any shifted one, right, and you use the estimator of the action value from that one, you still compute the right gradient of your policy network, of the objective, right? Everybody's clear? Questions? No question? So, moral of the story, you really do not need to work directly with the Q estimator. You can work with a shifted version of Q estimator, right? And this means that you can work with -1 to 1 instead of 10 to 12, and you are actually not harming anything in your training, right? You're still computing the right gradient. The only difference is that this one might be computationally more stable. Questions? No question? So if you got no question, then one thing that is left here, you might tell me, how can I find that U? I'm going to talk about this later. This is what we do at the end to get advantage, right? No worries, no rush. We're going to get there. No. So this is the more general version of the policy gradient theory. So what it says that if you want to really have the gradient with which you are updating your policy network, well, take the expectation of this guy. Your Q minus some U, you don't care what that U is, times the gradient of the log likelihood. Still, you are just working with the gradient of log likelihood, right? But that term that is getting multiplied, you now have this degree of freedom to shift it as you wish, right? Clear? So you can shift it as you wish, and this is what we call it baseline. Right? This U term is what we call it baseline. It's like you look at your Q, and then you would say, okay, I'm going to put the baseline, right? In the example we had, or Q, when we are working with a system of rewards between 10 to 12, we put the baseline to be 11, right? Then the Q estimator that we get is around 11. It's going to tell me how much different this is from the baseline. If I am around 10, I am below the baseline. I'm going to get something negative, right? If I am around 12, I'm above the baseline. I'm getting something positive, right? This is still giving me the right gradient that I want. Okay? So that means if you want to just play with your policy gradient method, you can add a baseline simply to it. So when you are sampling one trajectory, then say you are doing some estimation, Monte Carlo, whatever, you get your estimator of Q, then you can have one baseline. And that baseline could change from one point to another, right? It's not important. The only thing is that your baseline should not depend on your action, right? It can depend on your state, right? But as I said, no worries. I'm going to tell you what is the right choice of U. Can you guess what is the right choice of U at every single state? The value, great, right? Because value is the average action value, right? And then you want to know how your action value is different from its average, right? So you just concentrate it from its own, around its own value, right? So that is what we call it baseline. So the obvious choice is the value. You might say, why this is obvious? Well, simply because the value at every single state is giving us the average action value, right? So it's going to tell you if you're at this point, right, you can do this action, that action, that action. In average, you're going to get this value, right? Now you want to compare your action value with a baseline, so the best baseline is that average value, right? So this means that in practice, you typically put your baseline to be this V itself, right? And this difference between the action value at action A and value and state S with the value of the state, this is what we call it advantage. Okay? We want to see if we are in this state, every single action that we do, how much advantage it gives us as compared to the average value we get. Clear? Everybody's clear? Now, my apologies, I have a very bad notation here. U is again showing up here, right? But this U is not the previous U, right? This is the difference. I'm sorry for that. Don't get confused. This U is the difference between these two, right? Because I showed this guy by U initially, but yeah, it's a confusing notation, I accept. So this is the difference between these two, okay?
Should be Q star, Q dash, right?
It's a Q prime, right, right. It's the Q prime, correct. Everybody's clear? Questions? No question? Okay, great. So if you got no question, just let me give you a bit of visualization about the advantage. What does advantage mean? Say this is, you are in one particular state S, right? And in this particular, you know that if you do the first action, you're going to get this much value, this much expected return. If you do your second action, this is the value you get, third action, fourth action, right? And then what is the average value? Well, this is the summation of these guys divided, for example, by 4, right? If you assume that every action is happening with the same chance, right? And then the average value is, for example, 0, right? So then here in this example, your advantage is exactly the same thing as your action value, right? Because in average, you are going to get 0, right? And the value you see for every single action, it simply tells you how much better than 0 you are going to do, right? If you do action 2, you're going to do very, very worse than average, which is 0. If you do action 1, you're going to do much better than the average, right? Correct? Now, but if you have such a case, like every single action that you do, you're going to get a positive value. But some of them are more, some of them are less, right? The average value is now more than 0, right? And then the only thing that advantage does is just centralize everything around this new value, which is not 0, right? So this is going to be your advantage, right? It's going to tell you, okay, doing action 1, you're going to get this much better than average. Doing action 2, this much better than average, and so on, right? So obviously, your advantage should always have some negative values as well, right? So for some actions, it's negative. For some actions, it's positive. And you're going to add up to 0, right? Average to 0. Everybody's clear? Questions? No question? OK, so this is the one which you find in the textbooks. They call it like policy gradient with advantage. It simply is the one I showed you with baseline. For the baseline, you just put the value function, OK? So this means that when you are sampling with your trajectory at every single state and action that you are, you just estimate the action value, you estimate the value, you subtract them, this is your advantage, then you update. Questions? No question? Yes.
Sorry, so before you said about something averaging to 0, did you just mean the value, or did you mean the advantage?
Once again, real quick.
You said something would average to 0.
Advantage.
Okay.
It's always advantage. Average is to 0, right? Because if you look at it, the expectation of this guy is value with respect to A, right?
Yes.
So if you average the advantage with respect to A, your actions, it's going to be 0. If you average it with respect to action, it means that you multiply everything with your policy, and then you integrate it over A, right?
And then every single term here will.
No, for every single action, it's going to be 0, right?
Okay.
Sorry, for every state. For every single state, it is going to be 0.
I think that makes more sense.
Yeah. So at every single state that you are in the environment, you're going to say, what is your average value in this state? And then you would say, okay, how much advantage I get by doing different actions, right?
And then if you took all of them, that would.
Average, it should be 0, right? Because some of them give you positive advantage, some of them give you negative advantage, right? It should be always the case.
That makes sense. Thank you.
So everybody's clear? Questions on that? No question? Okay, so yeah. Now I think we are out of time, so I cannot really. I think there is not so much left here. Right. Yeah. It's just actually nothing left. Okay. So this is the case. This is the final algorithm. Sorry. So this is advantage PGM. So in every single time, you're going to compute the value, you're going to estimate Q, and then you're going to just compute the advantage, right? Now, one thing that is here a question, you might say that, how can I compute the value? Well, since you have your policy network, right, you just need to average your action value with respect to the action, right, with respect to policy. And that is not a problem. You can do it. But we're not going to do it at the end. It's going to help us a lot. Just to give you a quick hint here, this Q term, if I write down the Bellman equation for it, how does it look like? The immediate reward plus future value, right? V, not Q, right? You remember that, right? Now, if you think about that, this is going to be the immediate reward plus next value minus your current value, right? So you actually do not need to work with the Q at all. You can just simply work with value, right? You see it? So you need to work with the estimates of value, indeed. You don't need to work with the